A body oscillates simple harmonically according to the equations x is equal to 6 6.0 cos of 3 pi t plus pi on 3 meters in meters. What is A? The displacement, B, velocity, and C, acceleration at time t is equal to 2 seconds. So
there's $2,000.
We are given time to determine displacement, velocity, and acceleration. Okay. Yes, we have velocity when you are given displacement, and acceleration formula when you are given displacement as well. But this time around, we are given time to calculate the displacement and the velocity and acceleration. So please note the difference. Note the difference. Let me put the last notice on the platform again. Now note that come in. Note that I said equations of a body executing simple harmonic motion can be x is equal to a cos omega t. If it is this, then it means that the wave or the simple harmonic motion only starts from the mean point, or starts from the mean point, or it starts from the equilibrium position. Equilibrium position. If it is x is equal to a cos omega t plus or minus a phase angle phi, then it means that it is either starting towards the mean point or away from the mean point. So it's either starting towards the mean point or away from the mean point. Note these two differences. So when the angle between, if we have cos omega t minus phi, then the wave is moving away from the mean point or the first point. If you see cos omega t plus phi, then it means the wave is moving towards the mean point. Whatever equation you are given, you must work with it. And I'm saying this because I saw a lot of you changing the equation that was given, x is equal to 6.0 cos 3 pi t, just and assuming that pi over 3 is 0. So instead of this, they use 6 cos 3 pi t to solve the question. When you do this, you have changed the original question you were given. So take note. You must work with what you are given. Class, are you okay? Are you okay?
Please, can you come again?
So what I'm saying is that when you are given the equation, you must work with what you are given, either plus or minus, or when the wave is equal to starting from the origin. So you work with whatever equation you are given. You don't assume that part of it is zero, and then use the kind of equation which will be comfortable to you. Are you okay?
Yes, please.
So we are given this equation, and once it's plus pi over 3, which is also 60, angle of 60, it means that the wave is moving towards the mean point, because the operator separating them is plus, is moving towards the mean point. So to determine the displacement at t is equal to 2 seconds, all that I do is that substitute the time given to you into the equation. So wherever you see t, substitute 2 plus pi on 3. So you have 6.0 cos of, this is 6 pi plus pi on 3. Add them. They are like 10, so add 6 pi plus pi on 3 would give you 19 pi over 3. Okay, this, whenever you have an angle, note that the number in front of the cosine is always an angle theta. You can change the angle in radian or in degree. If I want to solve this in radian, all that I need to do is that substitute the value of pi. Take pi to be 3.142. And divide by 3. So please, can you work the expression within the bracket for me? 19 times 3.142. Nineteen times 3.142 divided by 3.
$19.8993.
Okay, so this is 19.899. At least I'm writing it in 3dp. Now, meaning once expressing it in 19.89 means that theta is in radian. So you find cos of 19.899, but you must ensure that your calculator's angular measurement is in radian. Okay, so change it to radian if it's not in radian. So after changing this, then input cos 19.899. That would give you approximately 0.5. So 6 times 0.5. The value there is 0.498, but we can run it to approximately 0.5. So 6 times 0.5 is equal to 3 meter. So it simply means that at t is equal to 2 seconds, the displacement is. If I want to have my calculator angular measurement in degree, and work with it. That is also doable. Meaning we must change 19 pi over 3. 19 pi over 3 to degree. I want somebody to do that for me. Change 19 over 3 pi to degree. 180, pi is equal to 180 degrees. So change 19 over 3 pi to degree for me.
If you get 0.035
no,
1
no, you are changing 19 over 3 pi or 19 pi over 3 to angle in degree. This is in radian, don't forget. You are changing it to degree. Please, if
I had 1,140.
that's correct, 1,140, that's correct. So please just substitute. Glenn, please mute yourself. Knowing that pi is 180, just 19 over 3 times 180 degree, and that will give you this. So x can also be equal to 6 cos of 1140 degree. And this time around, let your calculator be in degree. So change it from radian to degree. Then input cos of 1,140. That is equal to half. Okay, so 6 times half would give you the same value, which is 3 meters. So whichever way you look at it, you must get the same result. Please, is that okay? Class, are you okay?
Mr. Edia, please. You see, we solved a certain question before you gave us this assignment. And for that one, we assume the pi to be 0. So how come this one you're saying we should not assume it?
Oh, if you can get me the question, I'll be very glad. Okay, because if it is there, you cannot assume it to be 0. You get it? So if I try and then get me that question you are referring to, and I'll address it for you. Okay.
Please try send it to you.
Yes, right away. Or if you can just say it, so I write.
The displacement equation of an oscillator is given by is equal to 5 sine and then into bracket 0.2 pi t plus 0.5 pi. Calculate the period of oscillation.
Calculate the period.
Yes, please. Of oscillation.
Here, you see, you can understand why you are saying the period, in determining the period, it has nothing to do with the phase constant, which is 0.5 pi. When we compare this to, this is A sine omega t plus kx. We are looking at waves. You understand this better. So in determining the period, it has nothing to do with kx or 0.5. All that I do is that omega can be obtained from, period can be obtained from omega. So you equate omega to 0.2 pi. And knowing omega to be 2 pi on the period, you can determine your period from this. Is that okay? So maybe either I said or you assume that because in determining the period, it has no relation with 0.5 pi. Is that okay?
Yes, please, Andy.
Okay, thank you. Please, just as Erefa has done, if you have any concern, do not keep it. Bring it up so we address it. Okay. The more we do that, the better we become. The last question says that we have to find the velocity. And velocity is equal to the rate of change of displacement with respect to time. Meaning that to get the velocity, we must differentiate the velocity, the displacement equation, which was given to us, 6.0 cos what? Cos 3 pi t plus pi on 2. Okay, and this is, we can do this by like assuming that x is equal to a cos omega t plus phi. Okay, we can create a general equation which is similar to this. Okay. Hello.
Please, it was pi on 3.
Pi on 3. Thank you. So pi on 3. If you have an equation like this and you want to determine the velocity equation, this is dx on dt. So this will be equal to the differential of the x, which is a cos omega t plus phi. And when we differentiate this, this will give us a would not be affected. So a out, omega out, then into bracket negative sine of cos, negative sine of omega t plus phi. So that the velocity equation will be equal to negative a omega sine omega t plus the phase angle. All that I'm saying is that if we differentiate what we are given, we'll have the amplitude is 6. So 6, negative 6 times omega, which is 3 pi, times sine of 3 pi t plus phi. When plus phi, which is pi over 3. So when we differentiate the displacement equation with time, this is what we will get. Minus 18 pi sine of 3 pi, and we are to determine the velocity at time t is equal to 2. So put in the time, 2 plus pi on 3. Note that the phase angle will not change. Okay, we'll still have V is equal to negative 18 pi sine of 19 pi over 3, which is the same as the angle change in degree, 1,140. And what is the sine of 1,140? Please do that for me, sine 1,140. Make sure your calculator is in degree. This is root 3 of 0.86, which is equal to root 3 on 2. So multiply this by 18 times pi, which is 3.142. And this must give you approximately negative 49. Negative 49 meter per second or negative 48.98. Okay. So this will also be the velocity at the time t is equal to that. Class, are we okay? Then the acceleration. Acceleration A is equal to the differential of velocity with respect to time. So the V on the T. So it means to get acceleration, we must differentiate the velocity function, which is negative A omega sine omega t plus phi. I'm using the general formula so we can apply it to our given equation. So the coefficient A times omega will not be affected. So A is equal to negative A times omega. When you differentiate omega t, you get omega. And when you differentiate sine omega t plus phi, you have cos omega t plus phi. And so this will also give us negative omega squared times the amplitude cos of omega t plus the phase angle. And when we compare it to our velocity function, which is this, it means that, which is this one, it means that the acceleration equation will be square of the angular velocity, which is 3 pi squared negative times the amplitude. The amplitude is 6. Please, who is here, mute yourself if you haven't muted. Times the amplitude, which is 6, times the cosine of the same thing, 3 pi t plus pi on 3. So substitute, we are looking for the acceleration at time that. So minus 9 pi squared times 6 cos of the same 19 pi over 3. The phase angle will not change. And what is 9 times 6? 9 times 6. This will give us negative 54 pi squared cos 19 over 3 pi, or 1,140 is equal to half. Okay, therefore the acceleration A would be equal to negative 27 pi squared. I'm referring to, okay, 54 divided by 2 is 27. So negative 27 pi squared, exactly negative 27 pi squared. So let's square pi and multiply that by 27. So 3.142 the squared, okay, times 27. This is giving us 266.5. So A is equal to negative 266.5, okay, meter per second squared. So that's the value of the acceleration. Not so difficult, but you need to understand this principle of differentiation and apply. What's the next question? What's the next question under the same concept? Au revoir.
Mr. Edia.
Mr. Au revoir.
Mr. Edia, please, I want to ask that, does this mean that for, like, there's a different velocity equation for all the displacements, because when we were finding the
exactly, because when the oscillation is vertical, don't forget the displacement equation is A sine, and when the displacement equation is horizontal, we had x is equal to A cos. So it actually depends on what you are given. But the good news is that whether horizontal sine, whether horizontal, which is in cosine, and vertical, which is in sine, the maximum value will be the same for amplitude, velocity, and acceleration would always be the same, whether it is vertical or horizontal. Are you okay?
Yes, please.
Okay. So the next question is find also the phase constant. The phase constant is what adds to omega t, and so pi over 3 or 60 degrees. As for the rest, we'll not waste time about it because they are so simple. Find omega, blah blah blah. I'm not wasting time on it. Okay, because on those questions, almost everybody who submitted the work got it right. Class, is there the need to go through it? The other questions, sub questions. Let me have your views. The question 2 and the other sub questions, do we ignore it and move on?
No, please.
We should go through it.
Yes, please.
Okay. All right. So what's the sub question under what we've just saw? Calculate what? Oh, please do this with me so we can save time.
Please find also the phase constant.
So the phase constant is 60 degrees or pi over 3. And what's the next question?
The frequency and then the period of the motion.
Okay, so x is 6 cos 3 pi t plus pi on 3. Frequency can be obtained from, so when we compare this with A cos omega t plus phi, we can say that please phi is equal to pi over 3, which is 60 degrees. And so this is the phase constant. And then the frequency can be obtained from when you compare omega to 3 pi. Omega is 2 pi f. So 2 pi f times 3 pi, and f will be equal to 3 on 2 or 1.5 hertz. And the period, there's a relationship between frequency and period, which is this. So once we have the frequency, we can easily determine the period. Okay. So 1 divided by 1.5. What is 1 divided by 1.5?
0.667.
0.667 seconds. All right. Then the next question. If I read the next question for us, so we can do that quickly.
We stay there, please, after.
Please, whoever is ready.
An oscillator consists of a block of mass 0.5 kilograms.
So the mass is 0. Okay. Go ahead.
When put into oscillations with amplitude 35.0 centimeters. The oscillator repeats its motion every 0.5 seconds.
So it repeats its motion every 0.5 seconds. So clearly this is the period.
Yes, please. Find A, the period.
So
B,
we found
the
A.
frequency.
B, and hold on. F, which is equal to 1 over period, would also be equal to 1 over 1.5. So 1 divided by 0.5 is equal to, this is equal to 2 hertz. I had the next question, C.
C, the angular frequency.
Angular frequency is the same as angular velocity. Omega is equal to 2 pi f. So 2 pi times 2. So we have 4 times 3.142, which is equal to 12.485, right? 68 radian per second. We'll for the next question.
Then D, the spring constant.
Spring constant K is equal to M times omega squared. So once we have M is 0.5, omega is 12 point, is it 12 point? Check this for me.
12.68.
12.4.
568
squared. The answer must be there. What's the answer? Square 12.568 and multiply that by half. If you are talk, if I talk, Joe, yes, what's the answer?
is 315.91.
315.
Yes, please.
0.91 or 9 Newton. What's the unit? Newton. What's the unit? Newton. Hey. What's the unit of spring constant?
Newton per meter.
Newton per meter. Okay, what's the next question?
E, the maximum speed.
Hello.
So yeah, please, the spring constant, when I did the calculation, I had 78.9773.
Let's all confirm. Let's all confirm. 12.56 squared times the mass. What's the mass of the spring? 0.5, right? So let's confirm. What's the confirmation? Hello.
He's also got 78.98.
Yes, please, refer check it. It's 78.98. Okay. So correct it. And that's why, yes, that's what I actually like. Let's all be part of what we are doing. If there is a mistake, we all correct it. We all share ideas. Okay, and that would help us manage the time properly. Okay, what's the next sub question?
Please, the maximum speed.
Maximum speed. Okay, Leonard, speak. maximum speed V max is equal to angular velocity times the amplitude. So angular velocity is 12.568 times the amplitude. Please change the amplitude to meter. So 0.35. What's your answer?
It's a hot 4.3988.
4.3988. So approximately 4.4 meter per second. That's correct. What's the next question?
Please, the magnitude of the maximum force on the block from the spring.
Okay. So maximum force F is equal to K times the displacement. But this displacement is equal to the amplitude. I just want to upload attendance. So K is 78.98 times an amplitude which is 0.35. So I'll put that together for me. $78.98 times 0.35. Frida and Refo and Co talk. Mami ya.
Is 27.64.
27.6 what?
43.
This is Newton. So this are the solution to the problem. Is there any question? Is there any question?
Nope.
No, please.
Okay. Then let's continue with our wave motion. So a wave is a traveling disturbance that carry energy from one point of a medium to another. We defined a wave motion last time. Any traveling disturbance that carry energy from one point of a medium to another. I'm coming. So a wave actually transfers energy. Wave motion transfers energy, but not matter. So when you visit the seashore or the beach, okay, that constant curvy thing which appears on the surface of the ocean is the ocean wave. And what you see is not actually water which is pushed to the shore. but it is actually energy traveling through the water medium. And what is the source of this energy? The source of this energy is energy from the wind or the windstorm within. So a wave, any form of wave transfers energy, but not matter. No, that is why our people have the old saying that the seashore never gets flooded. The seashore will never get flooded because whatever you see to be constantly pushed there is not actually water, but it is energy from the wind. Let's look at types of waves or examples. One example of a wave is what I've just mentioned, the ocean wave. We also can talk about the tidal wave. We have wave on a rope. Wave on a rope. We have sound. We even have water wave. When you drop pebble or gravel in water. Ruben, please mute yourself. Yansawakwa. Yansawakwa, I'm listening. Hello, Yansawakwa, oh, it's a mistake. Okay, so water wave. 4, we have sound wave. 5, we have earthquake wave or seismic wave or the earthquake. Six. Six, we have gamma ray. X-ray. Ultraviolet. We have visible light. Infrared. Microwaves. Microwave. Radio wave. Then we have television or TV signal. And other examples or types of waves. So these are the various different types of waves. Water wave. How is water wave different from ocean wave? You see, when you drop a pebble or a stone in water, that circular thing which is created on the surface of the ocean, when you put water in a basin or bucket, and then you drop a stone or water, a pool of water. When you drop a stone or a pebble within, that circular round thing formed on the surface is water wave. Okay. So these are the various examples or types of waves. Now, waves can be classified into many groups based on certain key observations. So apart from this type, we have what we call classification of waves. So under classification is about grouping. We are grouping waves based on certain things they have in common. So all these examples are being put under one body or different bodies or umbrella based on certain things they have in common. So the first classification sought to look at how this, the first classification looks at how the waves, the different types are propagated or transmitted from one point to another. Okay, so this classification is known as, so we are, under this classification, we are looking at mechanical waves, and electromagnetic waves. So mechanical waves and electromagnetic waves are classifications of waves. They are not examples. The examples are what has been listed. Okay. Now, what is a mechanical wave? A mechanical wave is any wave which requires a medium to be propagated. So a mechanical wave require a medium to be propagated. What it means is that hello, can you hear me?
Yes, sir.
Okay. For mechanical waves, if there is no medium, they cannot be propagated from one point to another. So, Mamiya, a mechanical wave requires a medium to be propagated. Example, without the...
Yes, please.
Without the ocean, where is ocean wave? If there is no ocean, we cannot form ocean wave. If there is no water, we cannot form water wave. If there is no ground or earth, where can be earthquake wave or seismic wave? If there is no air particle, there can be sound. So all, Michelle, I'm coming. all waves that require a medium to be propagated from one point to another are grouped under mechanical waves. Yes, Michelle?
The area, so it doesn't mean that all waves are mechanical waves.
No, all waves are not mechanical waves. So we'll look at, we've listed types of wave or examples. We'll look at those ones which fall under mechanical waves. Okay. So one, under this classification, we can talk about ocean wave, wave on a rope. If there's no rope, who are you? Okay, if there's no rope, there wouldn't be a wave on a rope. If there's no water, water wave. If there's no air, no sound wave. If there's no earth, earthquake or seismic wave will never exist. So all these examples fall squarely under mechanical waves. So they are mechanical waves are groups or classification of waves that require a medium to be propagated from one point to another. And I've given you examples. Then electromagnetic waves, also termed as EM waves. Electromagnetic waves or EM. These are waves that, please, if you haven't muted, do so. I'm getting feedback here. Glenn, please mute yourself, okay? So for EM waves, they do not require a medium to be propagated. Electromagnetic waves do not require a medium to be propagated from one point to another. So the visible light we get from the sun is an example under this classification. Okay, sun is a space, but in space we have points of no air. We have different spheres. We have stratosphere, strobosphere, we have ionosphere. Okay, there are different spheres before it comes to a layer where there is air known as the atmosphere. So the light, visible light, could travel through all these spheres and still get to us. So it's an example. All the waves from gamma ray, S-ray, ultraviolet, visible light, infrared, microwaves, radio waves, TV signals are all electromagnetic waves. So they are called EM waves. Okay, please, starting from, because we've listed, and that's why I'm not going through them. So starting from gamma ray down to TV signals, they are all electromagnetic waves. They are actually grouped under the electromagnetic spectrum. They have certain things in common. And one thing they have in common is that they can all be propagated without a medium. Two, they all travel at the same speed, which is 300 million meters within 1 second. Okay, so that's the key properties of EM wave. Please, is there any question? So look at microwave. We use microwave for long distance communication in telecommunication, telcos. So the wave that is used in sending out our voices, data. Okay, microwave. Now, before the development of fiber technology, if you want to talk to somebody outside Ghana, in US, UK, and other countries, before fiber technology, your call must be picked by the nearest, maybe MTN, okay, Vodafone or whatever network. It must be picked by their mast or the transmitter. So the mast picks it, sends the signals all the way to Kuntunsi satellite station. There is a very big satellite mounted at Kuntunsi near Pokwase in Accra, and that is what is responsible for calls moving outside Ghana. So all calls moving outside Ghana is given to the Kuntunsi satellite station, which is directed to the sky. It communicates to a satellite in space. So your call will be given to another satellite in space. The space one has the main office in US. So all calls moving outside Ghana will be sent to US, and the US will look for a destination of the call. So funny, if you are before fiber, if you are calling somebody in Togo, your call must go to US before it comes back to Togo. If you are calling somebody in Cote d'Ivoire, your call must go to Cote d'Ivoire before it comes back, must go to US before it comes back to you. Yeah. And that explains the reason why calls going to African countries are very expensive. Okay, if you are the credit or the data to talk to somebody in US for 3 minutes, you can only use that to talk to somebody in Togo for 1 minute, and this is the reason why. So look at the journey of the call. From Ghana, it will go to space where there's no air particles, yet the call will be able to go and then be given to a satellite, and it's delivered to a station in US. Okay, and that's how come, yes, matches will be played in Europe and other countries, but through satellite transmission, will be able to get it and watch, because this kind of waves do not require a medium to be propagated. Please, is there any question? Is there any question? If you have one, quickly do so. If there is no question, then we move on. Jojo, Mamiya, is there any question? Eva. Okay. Then let's look at another. Jojo, is it yes or no?
No, please.
Okay.
No, please.
All right. Let's look at another classification. We have transverse waves and longitudinal wave. Longitudinal wave. So the first classification looks at the mode or the means by which the wave is propagated from one point to another. This classification looks at when the particles of the medium vibrate, how is the energy propagated or the wave propagated? Don't forget that propagation of the energy is what we are calling as the wave. So when the particles of the medium vibrate, how is the energy propagated through the particles? And that is what we are calling as the wave, okay? So transverse and longitudinal classify, or this classification looks at the style of vibration of the particles, and when the particles vibrate, how is the wave generated? Don't forget, the beginning of a wave is the vibration of the particles of the medium. So the particles must first vibrate before the wave is generated. So in transverse wave, under this classification, you see this 0, 0 or O things or shapes I'm drawing. They represent the particles of the medium. So these particles of the medium can be vibrating in that up and down manner. So their style of vibration is that let's jump up and down. While the particles vibrate in that up and down manner, the wave is propagated through the particles in this manner. So particles, you just jump up and down, and the energy which is channeled through you would go in that direction, which is perpendicular to the particle vibration. So this is wave propagation or energy propagation, and this line is vibration of particles. So we have vibration of particles. So in a transverse wave, we define a transverse wave as a wave, or in a transverse wave, the vibration of particles of the medium is perpendicular to the propagation of the wave. In a transverse wave, vibration of particles of the medium is perpendicular to the propagation of the wave. So they create this relationship where the vertical is the vibration of particles and the horizontal is propagation of the energy or the wave, and they must be perpendicular to one another. All electromagnetic waves fall under this classification. So all electromagnetic waves, let me shorten this, EM waves, all EM waves are transverse wave or fall under this classification. In fact, the name electromagnetic is even derived from the fact that these waves have electrical and magnetic properties. And the electrical and magnetic properties are perpendicular to one another. So all EM electromagnetic waves from gamma ray down to radio waves fall under this classification. Please, are we okay? Then under this classification, we have wave on a rope. Wave on a rope. Earthquake or seismic wave. Or seismic wave is also. Then water wave. Water wave and wave formed on the surface of the ocean, or ocean wave. Ocean wave falls under this. Then longitudinal wave. In longitudinal wave, particles vibrate in that back and forth manner. So particles vibrate in that back and forth, and the energy or the wave is also propagated along that same direction. Okay. So whilst particles vibrate in that back and forth manner, the wave is also propagated along that same direction. So we say that in a longitudinal wave, particle vibration is parallel to the propagation of the wave. In a longitudinal wave, particle vibration is parallel and is parallel to the propagation of the wave. And an example, longitudinal waves are not many. One key example is a sound wave. So sound wave is an example of a longitudinal wave. Then we also have waves formed at the deeper parts of the ocean. Deeper parts of the ocean or water bodies. Are examples of, if the wave is formed at the shallow part, the surface part of the ocean or water bodies, it is transverse. But when it is formed at the deeper part of it, we have. Please, are we there? Everybody is quiet.
Yes, please.
Okay, any question? I've talked for some time. Come in too. So I regain energy and momentum. Any question?
No, please.
No, please. No, please. Okay. Then let's look at the wave profile. The wave profile. How does a wave look like? God's love.
So please, so with the transverse waves, it means that all the electromagnetic waves are transverse waves, but just some of the mechanical waves that can be found under the transverse waves.
Yeah. So you see, God's love, don't miss the two classifications. We have mechanical and electromagnetic waves. They are there for the sake of the means by which the wave will be propagated from one point to another. So every wave which will require a medium to be propagated will fall under mechanical wave. if a wave will not require a medium to be propagated, you fall under electromagnetic waves. Now, for transverse and longitudinal, there are also two different classification modes. And here we are looking at the pattern through which the particles of the medium vibrate. As against when they vibrate, how is the wave or the energy propagated through them? Okay, so in a transverse wave, particles vibration is perpendicular to propagation of the wave or the energy. So we go back to the same examples of waves and then put them under this classification as well. So we are saying that all electromagnetic waves are transverse waves, and only some waves and waves formed from the deeper parts of ocean or water bodies are longitudinal waves. Okay. There is a third classification, but which we must talk about, but we'll look at them individually, and that is progressive wave and stationary waves. But we'll come to this individual, there are subtopics under waves. That is why I'm not talking about them. Okay, so please just understand it from this perspective that we have classifications or groupings of waves: mechanical and longitudinal, and another classification which is transverse and longitudinal. And we are just picking these examples listed and then placing them under these two different classification styles. Gosla, are you okay?
Yes, please.
Okay. So the wave profile, how does a wave look like? A wave is a repeated function. All repeated functions are harmonic functions. Okay. So a wave is simply simple harmonic motion. So the wave motion is an example of a simple harmonic motion, meaning that any motion which is repetitive, any motion which occurs at a constant angular velocity. Okay, so a wave is a repeated something, and so it is also a harmonic function. So to draw something to represent a wave is drawn using sine graph or cosine graph. Look at so this is a cosine graph. Sorry, a sine graph. This is also a cosine graph. Sine graph starts from the origin 0, and cosine graph starts from the amplitude. So if you are given a picture of a wave, this is what you must draw. All harmonic functions are given this shape. Okay, so we say that a wave is sinusoidal. Waves have a sinusoidal shape. What this simply means is it has a sine shape or graph. So this is a photograph of a wave. So let's draw the wave profile. Let me use straight lines. and look at the measurable properties of a wave. So we are drawing a wave, the wave profile. This is the displacement of the wave. This is x. Please, the x, which is the horizontal, represents the equilibrium position of the medium. X represents the equilibrium position of the medium. And here, what does it mean? When the medium is such that there is no disturbance, external disturbance, there's no energy hitting the medium, okay, and the particles of the medium are at rest, that is what is denoted by X. So when there is no windstorm splashing the surface of the water, water molecules are calm, they are at rest, and their position is what is represented by X. Please, are you okay? Now, when the medium, when external energy hits it, the particles can be displaced from their mean positions by different margin. Particles can be displaced so much, others less from the equilibrium position. So the dot around the curve represents the displacement of the particles. So this means that particle can move so this margin, by this margin above X. Particle can also be moved. The energy can move it by this margin above X. This point indicates that particle can be displaced so much above X. Below is a repeated thing. You are jumping up and down. So this is a mirror of whatever is happening up. A mirror. So particle has moved below by this margin. Also by this margin. And particle can move below by this margin. Okay. So the wave represents the possible displacement of the particle above the equilibrium position at any time. Please, are you okay? Are we okay?
Yes. Yes, please.
Now, a point of upward maximum displacement of particles of the medium is given a special name. This is crest. So the free wave has points where particles have been displaced so much above, crest. Then we also have the same margin below, points where particles have been displaced so much but below, known as trough. So they are continuous. A free wave or free oscillation has this continuity of crest and trough. So the crest is defined as, the crest and trough are defined as maximum upward and downward particle displacement. The crest is maximum upward displacement. Of a particle. And it's not the whole, it's not this whole shape, which is called crest. No, it is just a point where a particle, I told you earlier that this point indicate particles. So where they've been displaced so much, so less, and all that. So maximum upward displacement of particle is what we are calling as the crest. And the trough is also maximum downward. Downward particle displacement. Also known as the trough. Check the spelling. Then the amplitude. The amplitude is a measure, a vertical measure from the equilibrium position to the crest or trough. Amplitude A, we have the same value below. But because it's below, along the negative x as it is negative A. Now we assume that for a free oscillation of a wave, a free oscillation is a continuous wave. I mean, everywhere.
Mr. Edia, please, can you come again with the definition of the amplitude?
Amplitude is the maximum displacement of a wave. The maximum displacement of a wave. So, you see, if the wave is continuous, traveling from 1.2 out, we assume that this height above the equilibrium position would be the same throughout. This height from the equilibrium position to a crest will be the same throughout as the wave propagates. Okay, it's a theoretical concept. Practically, it doesn't work, but we assume that for a free oscillation, a wave that is continuously traveling, its height above the surface of the water or the equilibrium position will be the same throughout. And that the maximum displacement from the equilibrium position is actually what we are referring to as the amplitude. But I said it's a theoretical concept. Practically, it doesn't work. All right. Then, so we are looking at measurable properties. We have seen the amplitude of a wave. Let's look at wavelength. Can somebody help me define the wavelength of a wave? What is wavelength of a wave? If somebody knows or if read something around that, please share with us. Anybody? The wavelength of a wave. No one. Mamiya. Okay.
So, when you have the crest and the trough, so after every successful crest and trough, one wavelength is formed.
Mamiya, did you say successful?
Yeah.
Why successful? What about the unsuccessful ones?
Okay, they're not successful.
So successive.
Successive, sorry. After every successive.
Or consecutive.
Yes, please.
Okay. Jojo, I have Calvin. Calvin, go ahead.
Say, after every complete cycle, one wavelength or one wavelength is formed after every cycle.
And what is a complete cycle?
Is one crest and trough.
Okay, so I'm getting two different views. Jojo, do you have something to add?
Yes, sir. Okay. After every oscillation,
okay,
one wavelength is.
Okay, so let me also come in with my view, and you can view it better. So Mamiya is talking about two successive crests or trough. Kelvin is talking about one full wave. And Jojo is talking about one oscillation. Now look at, I'm going to label points. This is a point A, the origin. Let's denote crest by letter C. Let's denote troughs by the letter capital T. So A, this is B. This is a point D. E. F. This is another crest. So let's even end here. Waves are similar to a complete cycle. So if you recall, when we're plotting simple harmonic motion, we're given angles. This is 0, this is 90, this point B is 180, this is 270, this is 360. If you are you there?
Yes, please.
What is 360 plus 90? 450, right? 450 plus 90. Let's hurry up. 450 plus 90.
540.
540 plus 90.
630.
And this is 270. Okay, so let's end at 270. This point A starts a wave. The point D ends a wave and also starts another wave. Point A and point D are or occur at the same angle. Why do I say that they occur at the same angle? The angle 0 is the same as the angle 360. But if you consider a revolution, one full revolution, this point is 0, 90, 180, 270, back to 360. So 0 and 360 occur at the same point. 360 plus 90, this is 450. 450 plus 90. 450 plus 90, 540. 540 plus 90, 630. Then back to 720. This point 0, 360, 720 are at the same point. They are the same angles. 90 and 450 act at the same point. They are the same angles. 180 and 540 same. 270 and 360. At one point act at the same angle, we say they are in phase. And that is why when you point sine and cosine of 0, 360, 720, it will give you the same value. Do it and see it for yourself. Input sine 360, sine 0, sine 720, or the cos of it. They will all give you the same thing. The same thing applies to 90 and 450 because they are basically the same angles. Okay, please have you confirmed? Do it for 90 and 450, 540 and 180, 270 and 360. And you see it for yourself. When you take the sine, the cosine, you get the same values. Okay. Please, can I move on? So it means that the angle 0 and the angle 360 occur at the same, they are the same angles. And the angle 720. Same to angle 90 and the angle 450. Same to the angle 180 and 540. Same to the angle 270 and 630. They are the same angle and act at the same point. And when points behave in this manner, we say they are in phase. So A and B, point A and B, A and D, sorry, A and D, and F are in phase, meaning they occur at the same angle. So if we say that points are in phase, they occur at the same angle and they vibrate together equally. Point 90 and 450 are also in phase. So they occur at the same angle. So CC are in phase. They occur at the same angle. Then 180 and 540. So B and E are also in phase. And T and T. And the distance between any 2 points that are any 2 consecutive points that are in phase would give you a wavelength. So technically or professionally, wavelength is defined as the distance between any 2 successive points that are in phase. Okay, professionally, wavelength, which is represented by lambda, is defined as the distance between any 2 successive points that are in phase. And when points are in phase, they occur at the same angle. However, because crests, successive crests, are in phase, that is why wavelength is defined as the distance between 2 successive crests. Because successive troughs are in phase, that is why it is also defined as such. And so if we can pick the shape of a full wave, can be A and D are in phase. A full wave has this shape. Let me draw it well. A full wave can have this shape. Equally, a full wave can also have this shape. This is crest, 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 another crest. A full wave can also have this shape. This is trough, trough. So when we are talking about a wavelength lambda, it can have these 3 shapes. This is successive crests, this is successive troughs, and this is starting from the origin to another successive point that is in phase with the origin. Please, are we okay? Class, are we okay?
Yes, please.
So, Mami, yeah, that is how that definition is coined from or count. The distance is defined as the distance between any 2 successive or consecutive crests or troughs. Is basically the distance between 2 points that are in phase. And when you understand it this way, you can locate a lot of points that are in phase, and every 2 distance between them must give you that. Eva, are you fine? Eva, Angel, Jojo.
Yes, please.
Okay. Wavelength is a length, so its SI units S in meter. What about frequency of a wave? The frequency of a wave is the number of successive crests or the number of 4 waves that is propagated within a given time. So the number of 4 waves or cycles that is propagated or transmitted within a given time. But we usually peg frequency, the time, for 1 second. So Frequency is the number of complete cycles of a wave within a second. Okay, the number of complete cycles of a wave propagated within a second, but it can also be at any other time, t. Still, F is equal to N over T. And the period, capital T, is our old friend, period. Please, SI unit of frequency is hertz. It was named after my good old friend, Heinrich Hertz. Heinrich Hertz, a German physicist. Okay. Yes. Nathaniel, we are far home. All right. Then period is the time taken, okay, for a complete cycle. The time taken to make a complete cycle or a complete wave. So it's not different from what we've seen in SHM and then in circular motion. Then the speed of a wave. The speed of a wave. Speed is equal to distance over time. Distance covered over time taken. Here, in determining the distance and the speed of a wave, we consider the distance covered by one cycle of a wave. The distance covered by one full cycle of a wave is equal to its wavelength, lambda. What is the time taken to make one full cycle of a wave? Yes. Mamiya, what is the time taken to make one full cycle of a wave? Mamiya.
Yes, please.
What's the time taken to make one full cycle?
1 over frequency.
So what is the time? What time will be taken to make one full cycle of a wave? Jojo. Nathaniel.
Is the period.
The period, which is capital T. If you are waiting to get a value, sorry. The time taken to make a complete cycle of a wave is equal to capital T, the period. Knowing that, so this is one way of determining the speed of a wave. Divide the wavelength by the period. Or, because F is equal to 1 over T, and V is also equal to lambda times 1 over the period, it means that this is also F, isn't it? So we can say that the speed of a wave is equal to its frequency times the wavelength. When we substitute F for 1 over T, we can say that this is the speed of a wave, F times lambda. So that's it. So we've looked at amplitude, we've looked at wavelength, we've looked at the frequency, the period, and then the speed or the velocity of a wave, which is SI unit meter per second. Please, is there any question?
No, please.
All right. Then if a wave has this shape, any shape has its meaning. Any shape. As students, Jojo, are you here?
Yes, sir.
Any shape has its meaning. If you have graph of motion or linear graph, and the graph is such that the shape is this, what is its equation? 2. I'm going to give you different graphs. If the graph is like this, what is its equation? If the graph is like this, what is its equation? And finally, if we have this, what is its equation? Yes, can somebody help me determine the equation for the first one? If you are not able to do that, then I have to report you to Mr. Hackman. Yes, who would help me write the equation of the first graph? A volunteer to help. Hey, if the volunteers are not volunteering, then I'll call you. Elsie, come and see, or else you will see Elsie. What's the equation of this first graph, Elsie? Oh, Elsie. Okay. Maybe Elsie is drinking water. So Efia, don't tell me you're also drinking water. You are not.
Sir, please, what equation, like, what are we finding for?
Equation of this graph. 1, 2, 3. Are they graphs which represent linear motions? Equation of a straight line
Yes.
graph? Yes. You agree with me? Okay.
Yes.
So what will be the equation for this straight line?
71 x is above 0, above the origin. So are we finding for like a quantity or just the graph?
The graph, equation of the straight line. I just want the equation of the straight line. Okay, Jojo, I put it to you. Jojo, help me write the equation for this graph. We have 7 minutes, so let's hurry up. Jojo. Mamia. Hello, Mamia.
Yes, please.
Okay, Calvin wants to volunteer. Calvin, go ahead.
Sir, please, why is it called term expansion?
This is y is equal to mx plus c. Okay, I agree with you. Jojo, what about Calvin, what about this one? The second one. Mamia, if you have seen something, you can also share. Please, whoever has seen something can share, okay? What's the equation of the second one? Calvin, over to you. Calvin. Calvin, are you confused?
So please, wouldn't it be the same?
No, it won't be the same. But what informed you this decision? What informed this decision?
So please, I think the second one, y is 0.
No, y is not 0. Y is the dependent variable. Okay, because of time's sake, this will be y is equal to mx. Just y is equal to mx because c is 0. The intercept on the vertical axis is 0. You gave me this equation because the graph cuts the vertical axis at the positive point, and that is what c is. Over here, the intercept, the graph cuts the vertical at 0. So c is equal to 0. Therefore, y will be equal to mx. Yes, the verdict is out. Somebody to help me write the equation for this one.
So that be y is equal to mx minus c.
Exactly. Minus c, because it cuts the graph vertical axis at the negative. Then Eva, this is for you. The fourth one is for you. All for you, Eva, all for you. Yes. What's the equation for this one? Oh, Eva, you are going to drink water. Angel. Angel. Oh, Angel is going to drink water. All right. Hey, Efia, back to you. What will be the equation of the last one? Oh, Jojo. Jojo, what's the equation of the last graph?
Yeah, I have
Oh,
for that one.
Oh, no.
Either it will be
Crispin is saying y is okay. Y is equal to c.
y is
Y is equal to c.
Yes, because over here the gradient the slope is 0. So if the slope is 0, then it's only cuts the vertical axis at a point. So assuming this point is 2, then it means that the equation of this graph is called y is equal to 2. Are you okay? So if any graph has an equation, this is a quadratic graph. Its equation is ax squared plus bx plus c. Okay, it can also be, a quadratic can also be this. All right. So if a wave has this shape, what is the equation of the wave? So the next thing we'll be looking at is that equation of progressive wave equation. A progressive wave equation. What mathematical expression can we use to represent the wave? That's the essence of the progressive wave equation. Okay, it's 11:58. I'm giving you 2 minutes for water break. Go and drink water and come back. In 2 minutes time. Bye-bye. So 1 minute for water break. Go and drink water and we shall meet tomorrow. Bye-bye.
Bye.
Okay. All right.